Hello, Krishna. Can you hear me?
Yes, sir.
So, in the last class, we talked about solenoid. We take the proof of a formula for like magnetic field inside the solenoid without using that previous laws. Basically, without using Ampere's orbital law. Krishna, did I give you the proof for the magnetic field in the solenoid using Ampere's orbital law?
Yes.
Alright. So now we are going to move to the toroid part. Let's talk about ideal toroid. Um, toroid is basically circular solenoid. What we need to do is just start from anywhere, maybe like this. This kind of structure. So you can assume this to be a toroid. It is not a just think of it as a toroid structure. This is going down. So current I is going to upside. This is going up. Okay, this is complete circular form, like this. So what we can do is um, let's I'll just simply make it into two ways. Like this is one, and that is another. Yes. So that is the thing. I'll just this kind of totally is there. Okay? From the center, maybe the this this radius is big. Also, like this kind of things are there. So what we need to calculate is we need to calculate the thing. If I ask you about the radius, you know it contains two different radius. It has two values of the radius, right? One is A, another is B. So if I ask you what is the minimum, like central, you can say that the central radius is this. So, you can call this as a central radius. Yes. So maybe I can call this as R min from this point to this point that you can make it as R. Okay. This is your R radius you can take. What is this radius? Because this is a mid of both, so this R is nothing but A plus B by 2 in general. When your solenoid is very thin, in general, we directly take it R equals to A or equals to B. When this is the distance between when B minus A is very close, when they are near zero, then you can take this. Otherwise, this is possible. That is one thing to take talk about. Otherwise, A plus B is much better actually, because when this they both are equal, then when they both are equal, then this will eventually come out as either A, either B. Okay, so this is the first way to do this. Now, if you see carefully how your magnetic field is coming out, you know, due to each coil, magnetic field is in the center, right? If you talk about this coil, magnetic field this way, this way, this way, this way, this way. So, what is the actual value of magnetic field? Can we actually calculate the magnetic field? Yes. How we are going to calculate this? Simple, dV. Krishna, can we actually calculate the magnetic field from here? Yes. Assume that in the total, n turns are there. Okay, and number of turns. If I ask you, Krishna, what is the length of this? You will say, sir, the total length of this is, in this case is 2 pi r. Okay, length is 2 pi r. So what is n? Numbered instead, you can say n by 2 pi. This is the total, this is basically number of turns per unit length. Turns per unit length. So because I at this point magnetic field is due to this reason. So what is how much is the turns are there? You can simply say n times of dl. So basically number of turns per unit length and dl. Even. Alright. So what is magnetic field? Mu naught times of I. Is it what the magnetic field is all about, or something else I should take? What do you think? Vedna? Should I take something else, or this is fine? So if you wanted to calculate, we generally do magnetic field due to a circle. This circle is nothing but how much? Can I say this is nothing but mu naught I divided by 2 pi r? Can I say this? I will explain you using Ampere circuit law. Also, Prerna, you are going to apply a Ampere circuit law, and I wanted to calculate magnetic field. I know if I take this portion, what I'm going to see. You know, for an Ampere circuit law, I simply say that B dot dl should be equals to mu naught times. What is my B dot dl? I am saying this is A, B, C, D, and 1. So you can simply make it into the four ways. dl plus bdl plus bdl plus bdl. Okay. So if in this case my current is going this way, from behind it is coming front side. Okay, it is coming front side. This is behind. So what kind of magnetic field I have? My magnetic field inside is this direction. So A to D, you can simply say A to B, B to C, C to D, and this is D to A. Although in this part magnetic field is perpendicular, so this AB will get cancelled out. CD is going to be cancelled out. What about BC? This is outside, so here magnetic field is zero. Okay, all 3 points are zero. This is because of the 90-degree angle, and this is because of the zero magnetic field. What about this part? This is basically A to C. Here you can simply say B. What is DL? So if I ask you about what is DL, how your DL is going to get integrated around it? Can I say for each magnetic field, when you are going to calculate, you are going to get DL, then this DL, then this DL, then this DL. So when you complete the fourth circle, you will be going to get 2 pi r. This makes you out mu naught times of r. From here, your final solution comes out as B is equals to mu naught I divided by 2 pi. Okay. Also, when you are covering the whole of the system, this current is not just I because you have covered a lot of things, right? So in that case, this will become N. Okay, that is it. Total N terms are there, right? So due to that, the current is this much. What is n by this? We can simply make it as mu naught I times. Is this clear? This is all about the ferrite chloride. If you see the formula for the chloride and this solenoid is the same, exactly same. There's no difference in between them. So yes, if you have any doubt, please let me know. Kirtan, any doubt here? All right, okay. So we are done with this part. Okay? And by this topic today, whatever we are going to discuss, after this we will be done with this chapter. So first thing we are going to discuss about magnetic field due to current carrying conductor in all long cylinder. Magnetic field due to current from hollow cylinder. Okay. First we'll discuss about the hollow cylinder, then we'll discuss about the solid. So assume I'm saying I have a cylinder like this, and maybe the straight lines I can put over here. And this is going to be basically downhill till infinity in one. That this kind of thing is there. So you need to calculate. Assume this is the center because there should be center of axis in the cylinder of this. This is your radius. You need to figure out what should be the radius actually. What should be the magnetic field? So there's two cases. What is the magnetic field inside it? Basically, if I'm going to take this as a loop. So if you see carefully, for r less than r, because I can't have any loop. Okay, you can't have any loop actually. If you go and take out any loop you wanted to move out, there's no current inside. So you can simply say B dot dl is equals to mu naught times of 0, which results to magnetic field 0. Inside magnetic field is 0. Okay. The main part is for r is greater than r. So if you just take this as a loop from center, this distance is r. So you can simply say B dot dl. If you complete whole circle, you are going to get B times of 2 pi r is equals to mu naught I. So because the total current is already captured in this current, right? I'm saying the total current going is I. So this is also B is equals to mu naught I divided by 2. Clear? Any doubt? If I wanted to say what is the graph, if you want to represent this into the graph will look like this. X distance, current is R. Till radius R, because this R is radius is increasing, right? So till R, the magnetic field is 0. Before this, the magnetic field is 0. Make it like this. The moment you reach R, just that, suddenly it will go up, and if you see it is inverse, so it will like this. Okay, now let me, if you have any doubt, please let me know first.
No.
If you understood everything, you know what we are going to do the next part, right? In this case now, this next part, I'm going to talk about the solid. Okay. This I did it for the hollow. Let's go for the solid. So now I have magnetic field due to solid, due to solid cylinder carrying current. It actually carrying current also. I was not able to write it. So it's something like this. Okay. So in this case, actually, what I'm going to do is assume this is your cylinder. This is important object. So please pay attention. This is infinite down also. This is actually infinite from both sides. So first let's calculate for r which is greater than equals to mean to say I'm going to calculate this time further after because you know if I'm going to make a random Amperian loop, okay, I'm going to get D, DL will be there, the small part, and I'm going all the current is going to get captured inside. So you can simply say B dot DL is equals to mu naught I is equals to mu naught I divided by 2 pi. This is for inside, outside basically. It's like that. The main twist is for inside. What if your current is inside? For this case, now let's say I'm going to talk about this one. Because this is a solid, it has all the portion is correct. So assume I'm going to take this as a small Amperian loop. If I'm going to take this as an Amperian loop, what I'm going to get? Just think of it. This is my Amperian loop. Okay? In this kind of Amperian loop, if you see carefully, what is the current is captured? Because this is where all the portion of charges are there, which is moving upside. Right? So you can see only this portion is captured. So whatever the magnetic field on this line will be there, that is due to the charge is there. Okay? So what I can simply say is this magnetic field will be here due to mu naught times of I dash. What is I dash? That is only the thing we have to calculate. So you can simply say that B times of 2 pi R is equals to mu naught I times of R. Basically current at value I. So B is equals to 2 pi R, sorry, mu naught I R divided. It is just a representation. It is not I multiplied by. It is just a subscript. What is the value of IR? So if you see carefully, let's talk about the current density. Current density is nothing but current divided by area, which is equal to I times of R divided by area also. So here maybe here. So what is the total area? If you see the total area is pi divided by pi r square. This is I r divided by pi small r. So this I r comes out as r square divided by r square. So what's the final formula you came come up with? Can you see this? Mu naught I r instead of IR, you can say this as I as it is. Sorry, it should not be like this. Yeah, here it will become reciprocal actually. This is IR, right? So IR becomes I times of R square divided by capital R. So this is what you do. So instead of this I, R square is there, R is bottom, so one will cancel out 2 pi r. This is the formula. Okay. If you see carefully, inside this is increasing. Why it is increasing? The moment you are increasing the radius, the current component is increasing. Okay? So if I ask you what kind of graph you are going to see, the graph will be very simple for this. We've already seen these kind of things in the electrostatics when we were calculating effect. Okay? So till value R, the magnetic field is going to increase directly like this. The moment you reach over here, this is going to get decreased. What kind of decrement it is going to have? This. basically square this. You can see this kind of a difference. You see your R value increasing, B is increasing. But what is this peak value? This peak nothing but B is equals to mu naught I divided by 2 pi. In this case also in the above case also. So mu naught I divided by 2 pi. Yeah, kid. So this is all two derivations we did. Please let me know if you have any doubt. If you are done, then we can actually move to the next.
Noted.
No doubt, right? Okay, I actually did this derivation in very fast forward manner. You see here, the thing was not. In this problem, if you see, my current density was constant. Mean to say, if I take this portion and from here, 4 electrons will pass in, okay, for this small area, it means if I increase the radius, uh, the corresponding on the dependency of this radius, basically by keeping this A constant, my electrons will be passing from here to maybe more quantity. But the things are going to get different if my this J is different. Okay? So here we are not discussing about the current density right now. They have taken very simple case and will be stick with this. Okay, so Kirtana, let's move to the next kind of problem. The next problem may be like this. Okay? In this case, you are given a hollow cylinder from some part, not complete hollow, but just some part is hollow. It means this may be the circle. Assume this is the inner part of it. This has a radius of r. Okay, let's call this radius of 2. Okay, for this point, for this thing, the radius is 2. Okay, this is basically a hollow portion and going to infinity. On the top of it, I have another cylinder which actually has bigger size. So basically, this kind of circle is there. So now what happens is there's two cases. If I ask you what is the magnetic field, so the thing is how you are going to calculate the magnetic field. The idea behind this is you know one thing that magnetic field in this part. Let's calculate. You can have three reasons. One is R less than A. Another is R is less than A, no, less than B. Basically, the very outer is less than B, but greater than B. Okay, basically, this reason. And the last one is R is greater than B. These three reasons are there. We have to calculate for them one by one. This is our task. If you understood the problem, let me know. So what we are going to do is let's do it for one by one. Is first okay. Let's do one thing. Let's do for r is less than. If you see carefully, B dot PL current is not there. Okay, so B comes out good. Here your magnetic field B is 0. What about R is greater than? It contains all possible current, okay? All possible. So this here you will be going to get B times of uh, what it should be. Formula should be mu naught I divided by 2 pi. Whatever the resistance you are, okay, this is standard. The main problem in crux is R is less than B but greater than. In this case, what is the thing you can do is do one thing. You know that current density is going to be same. So main part is I divided by E. If you see that what is the total area, I can say the total area is this part. Right? How much is this total area? If I ask you what is this total area, you can say, sir, the total area is nothing but pi b square minus pi a. So just put it over there. I divided by pi as it is b square minus a. Now, if I am saying, okay, let's do one thing. Instead of taking this kind of situation, but I'll just remove this part from here. Yeah. This comes out as I divided by IR basically, some random current at some distance because we are going from here at some distance R. Okay, chopping out dr kind of thing. Okay, dr kind of thing. So you are going 5, sorry, it should be actually removed IR divided by B square minus A square. For it should be equals to IR. What is the length of this portion? If you see carefully, this is nothing but a very small strip we are going to take off. Right? This strip has some width. That width is basically dr. So you can say that this strip is nothing but pi times of r plus dr square minus r square. This is kind of thing you are going to do. So if you just extend it out, at the end of the day, the result of this is going to be pi r square plus dr square plus 2r dr minus r square. So you can see cancel. This dr is very small, get cancelled. 2 pi r dr. This is what we are going to do. So let's remove it from here. Write the substitute over. The moment you do this, this becomes 2 pi r dr. So what is the value of I r? Pi divided by, sorry, 2 r dr divided by d square minus a. This is the value you are going to get. Now just go and put the value for any b. For any b, mu naught I. Okay, at some distance r you are, so that will be 2 pi r. That's obvious. What about I? This I should be like this. Okay, I 2 r dr divided by d square minus. Here, now from where to where you are trying to integrate, your r is going from a to b. So just put the value like that. So the moment you do go and do the integration for this, you can say, okay, your a has started from like basically your b has started from a and going to 5. So you can simply go and say mu naught I divided by 2 pi r 2 pi r divided by b square minus a square. Here you'll be having okay, this will be r square divided by 2, so it becomes 4. Sorry, it won't become 4. There's 1, 2, so this will get cancelled out. It will become r square minus a square. This is kind of formula you are going to get. Is it clear, Keith? So 2 pi r b square minus b square. This kind of formula you are supposed to do. But be careful the range. This is only value if you are into this range. Otherwise, the moment you r is greater, it should be b. The moment you reach either b or greater than b, okay, you need to apply this. This is also applicable when you are here. Okay? So these kind of things you have to be careful. And is it clear, Kirtana? Any doubt?
Sir, shouldn't the 2 be cancelled?
Uh, 2B, which one? Kirtana, which 2B?
2, sir.
Um,
The 2 from numerator and denominator.
this one, right? Okay, this one. Look, this 2 is cancelled out because when you are doing integration of dr, so it becomes 1 by 2 times so r square, right? So this 2 I consumed in cancelling out this. Is it clear now?
Yes, sir.
Makes sense? Any doubt is there?
No, sir.
Okay, did you understood this kind of pure concept? Look, it's very important to understand these concepts, okay? If you are clear, then we can actually move to one problem.
It's clear, sir.
Let's clear. Okay, so let's do one problem. I'll move to the next page. Look, again, because the things are very, what I can say, this is a part of your cylinder, okay? Just we are looking at from the top view. This is a top view of cylinder. Understood? So what kind of figure we are actually talking about? You are given another concentric concentric cylinder. Basically, two cylinders are there, where those cylinder the radius are concentric. In this cylinder, this portion is solid. Something like this. So here, let's something like this. Now what happens here is I'll just make this color quite dull, something like this. So no, let's do one thing. I'll just change this color and we'll say for out inside. Then we'll use this one and we'll say complete. Here in this yellow region, the current is coming upside. Let's say out inside. The current is going inside for this reason. In this green region, the current is going inside. Okay. Here it is coming upside. Then you have to tell me the magnetic field, the formula for the magnetic field at three regions. One is A, this is B, this is A region, A, B, and C. A, B, C mean to say that A, B, C can be anything. Okay. Let's do one thing. I'll try to increase the size so that it can look better. Yeah. So I may be remove. You need to calculate magnetic field at A region, maybe B region, and the last one is C region. The three points are there. So find magnetic field in A, B, and C region, where in yellow current is inverse. Magnitude is same, just the direction is different. And in green, um, outside, outwards, okay. And the region in between is empty. And if you want the values, I can say this is the center. From center to this is A, small a, small b, the last but not the least, small c. Okay. So yeah, Kirtan, that's the problem. If you want, you can try it once and let me know the solution first. Okay. So just think about how many cases I have given you and which cases you should, how you are going to solve it. That's your task. Please solve it and let me know the answer. Uh, Kirtan, are you solving this problem?
Yes, sir.
Okay, just do it once. Look, the way I have described the previous problem, same way you have to do. Okay. Take care of the directions carefully. You just need to look at the directions once. You will get that. Okay, tell me once. Can you access the board?
So
What happened?
the screen is blank, sir.
Uh, inside it does this all the PPTs which are what I can do now. Okay, look, you can do one thing. I'll end the session by here. Okay, you can try this as a homework part. Okay, I will share all 4 pages, and at the last page you will get this one problem. Okay. The idea is behind this is again same. I ask you about this, right? Who will be the responsible for them? Only this portion. The current lies inside this. So just think of some imperial law which have this thing. Okay, take all the current. Then same way you can go for B. But right now there's one thing. For B, some portion of current from this part plus some portion because this is complete. So some portion from here you will get. But direction is different, so you have to subtract it. When you talk about the outside, for outside you have to complete from here and complete from here. So you just have to do it. Okay. Here I am just saying one thing that current density is same. Okay. Current density is same all point is same as J. Okay. Now the problem becomes quite different. Okay. Just think in the terms of current density. If you will get it, is it fine, Ketan, now? I have written in the page, okay, that current density is same. So yeah, you can think in that term.
Yes.
If no, if there's no doubt you have, then I can end the session. If doubt is there, just let me know. First, I'll clarify your doubts, then we'll think of it.
No, no.
No doubt. Right? All right, Ketan, that's all. Look, by this, I have ended this chapter, okay. In the next, I'll be starting magnetism, pure magnetism. Okay? It's quite different thing, or induction, mix of the magnetism and induction. Okay, we'll discuss more about the magnetism properties, permanent magnet, electrostatic magnet, or something like that. We'll discuss those in later. All right, so yeah, that's all for the today's session from my end. Goodbye.